So today what I'm going to talk about is related to glasses, and glasses, I think there will be some aspect of active and passive glass. So I'm going to, so active glass active matter you already heard in multiple talks, and but this will be in a somewhat dense limit. Okay, so for the students, those who are expert can sleep little bit. For the others, this is the slide. I think it's important to tell what I mean by glasses. So if you take any liquid and you just basically cool it and don't give enough time to crystallize, then they go into a disorder phase, and in this disorder phase, basically. Yeah, so here is the liquid branch, and you cool, and then if you do it slowly, then there is enough chance that it will go into a crystal phase. But if your medium is complicated enough and you have frustration, then you may not easily get. Now it's dead. So you can actually bypass crystallization, and you will be in a regime which is called supercooled regime. And in the supercooled regime, you see interesting dynamical behavior. So in the high temperature, you see exponential relaxation, but as you go to the supercooled regime, you see multiple step relaxation process. One is fast relaxation, and then there is a plateau which appears. This is called beta relaxation. It's not a flat regime. So there you still see systematic decrease of the correlation function. And then eventually at a slightly longer time scale, the whole correlation decays. And this later part is called alpha relaxation, and there are a lot of interesting questions people are asking. Well, is there a relation between beta and the alpha relaxation, and all sorts of interesting questions, but let me not go into those details. So let me also tell you one interesting things about glasses. So when you go from high temperature to low temperature, this is an experimental data of selenium at a very high temperature to 900 degree and cooled to 250 degree. And if you look at these pair correlation functions, so they are basically shifted, otherwise it will be very difficult to distinguish between the data for high temperature and the low temperature, which tells you that you do not see much structural change. Actually, structural changes are very, very minute. But if you look at the relaxation time or the viscosity, it actually changed by factor of 10 to the 13 or 14. So such a drastic change in relaxation time without significant change in structure is what is a puzzle in glass community. And I think over last 40, 50 years or even more, people are really trying to answer these questions. What is it that leads to such a slow dynamics? So this is the part that I wanted to show, that this is the logarithm of the viscosity as a function of inverse temperature, and you see that relaxation time in various glass forming materials changes by at least 13 to 14 orders of magnitude, which is really dramatic, and one does not have a very clear idea why the viscosity or relaxation time changes by so much. And you don't see much changes in the structure. For example, like those who are familiar with critical phenomena, there also one sees critical slowing down, but there is a clear structural order which appears, and that's what drives to the phase transition. But here you have slowing down, but no structural ordering, and that's a puzzle which is with us for many years. And I don't want to claim that we have answered to any of this, but there are some progress made in last decade or so. So the one more interesting part is that there are few materials which actually show temperature dependence, which is more Arrhenius like, and there are many who shows actually non-Arrhenius type behavior, and depending on which branch they fall, those who falls into this Arrhenius branch, they are typically called strong glass formers, and the one which has a very strong non-Arrhenius behavior, they are called fragile glass formers. And I don't know whether there is any direct connections between this mechanical sense of fragile and strong, but I think I leave it that for discussion during tea and coffee. So when I talk about glasses, what do I mean? So there are many glass forming liquids that is part of our life, starting from metallic glasses, emulsions, colloids, that many of us, you probably heard from many of the speakers from last 2 days, I mean even today also morning with from Pavan. And then paint, and the large scale is this glacier formations and whatnot. So particularly in recent days, the glasses at very small scale became very important, and you see that there are many machines whose parts are made with this glasses, because they're useful if you, let's say, have a molten glass and you want to actually form this structure, then you can actually pour it in the mold, and then you do not have to do post-processing, because the glasses do not go through jump when let's say it solidifies in some sense. There is no density jump. So if you, for the crystal, there will be a density jump, and your the volume will decrease. So this leads to many surface defects, and one has to then do machine polishing or something like that. Also, you can create very nice pillar structures which can be used for various purposes. For example, here they showed that you can so this can be used for catalysis. So this is another aspect which look at extensively in our group. But today the focus will be primarily on something called dynamic heterogeneity, which yesterday we heard from Rajesh, and who else was saying, even Samriddhi was talking about dynamic heterogeneity in a turbulent regime. So in glass glassy systems, when I talk about heterogeneity, it means that if you look at various parts of the sample, then you see that there is a certain region which actually relaxes much faster than the other region. For example, here the red regions are the one where the dynamics is much faster, and then there are this blue region which does not change much. And this has been known for now at least around 15 years, that this is one of the main characteristics of glasses. So dynamic heterogeneity is an essential part of all glass forming liquids. Yeah, I think around 14 or 15 years ago, when I was doing my PhD, so this was one of the aspects which we wanted to understand. Can we understand or characterize dynamic heterogeneity via statistical mechanics? And so sometime before that, in 1991, Chandan and Sriram they proposed an interesting correlation function. They say that you do not look at 2-point correlation function, instead you look at 4-point correlation functions, and that may capture the dynamic heterogeneity or correlations building up in classes. So this is the same concept that I took it up when I was working with Chandan in IISc, and in 2008 or 9 we are able to show that if you take a glass forming liquid and compute these 4-point correlation functions, then indeed you can clearly show the growth of a dynamic scale appearing, and which tells you that so structurally you may not see many things which are changing, but dynamically there are a lot of things which are changing, and this dynamic heterogeneity length scale is considered one of breakthrough in understanding the physics of glasses. Okay, so if you want to know more about this 4-point correlation functions, and I'm not going to go into details of this, please read some of the reviews that we wrote in the last few years. And so today's topic will include dynamic heterogeneity, but in the context of active glasses, which is a non-equilibrium, because this conference is on non-equilibrium phenomena. So, but this is non-equilibrium, probably steady state. So this we may not, we are not very clear, because all glass forming liquid you never know whether you are actually, this is a steady state, or eventually if you wait for long enough, it will do something else. But in the regime which we are looking at, we do not see anything which is like phase separations or crystallization, but that I cannot rule out right now. So this is the work primarily done by my student Kallol, who is a postdoc now in Dusseldorf, and in collaboration with Saroj Nundi, we developed a mode coupling theory to understand some of the physics and the observations we have. So let me quickly, or maybe I can skip this. This many people have shown, but I think so. This is basically a swirling motion of this starlings, and you see that there is very nice formation of structures which, even though they do not have attractive interaction, they maintain this structure, but also is very, very dynamic. And then in 1995. Vistake came up with this proposal that if you look at very simple particle model where the interactions are only direction dependent, so basically they interact with each other by seeing the neighboring particles, and and they basically follow each other. So with that simple interactions, you can regenerate, you can basically understand some of this structure formation. And so there was some field study which was done by Giorgio Parisi in Rome along with his collaborators, where they looked at this I think Starling again in the central Rome station. This is Termini. And they videographed many boards and found the structures, and they were conclusively able to show that the interaction between two boards are more topological instead of metric. So basically it doesn't depend on the distance, but it depends on the orientation of various boards. And after he got a Nobel Prize in 2021, there was a nice cartoon which came up, and these boards are moving, and one board is asking the other, where are we going? And the other board said, oh, we are just following you. And the first board also doesn't have any idea where he or she is going. And everybody was confused, but that leads to the structure formation. So in a nutshell, active matter is a situation where you look at statistical mechanics of particle who has their own internal dynamical behavior. So it can you can have the thermal fluctuation as well, but this will be primarily dominated by the other motions that they can generate by themselves. Okay, and you can have computation of these active forces and along with the thermal force, and you can have plethora of interesting phenomena. And if you want to know more about this active matter, which become recently very popular among physicists and particularly statistical mechanicians, and you see there are so many talks on active matter. And so you should read the pioneering work of Sriram Ramaswamy and the review he wrote some time ago. Okay, so the why you want to study, so our goal will be to study active matter in the dense limit. So it is basically active glasses, and the motivation is that this kind of, there are many active matter component when they are in a dense phase, they show glass-like features, so which I am not going into details. Madan showed some data yesterday, but basically just to tell you that, so glass formations are so typical that if you don't basically do things precisely, you are always end up in glassy phase. So crystal formations are an art, but glass formations are basically going to happen all the time. So if you are just little careless, then you are into a glassy phase. And our idea was to look at this glasses with this active particle, but we are not going to look at glass with all particle active. We are going to look at glassy situations where there are some active particles along with other passive glassy particles. And this is the starting point was this work with by Rituparna along with Madan, Chandan, and also Pinaki got involved in the later stage. So what they proposed that you can actually have a typical glass forming liquid, which is this 80-20 binary mixture of well-known Cove-Anderson glass, and then you make few particles which are active, and then try to study their dynamical feature. And what they were able to show that as you increase activity, then basically you can fluidize the system. And they were also able to propose an interesting quantifier of activity, which is this quantity omega, which is basically the concentration of active particle, what is the active force that you are putting on each particle, and the persistence time. Persistence time is the time when this force will be acting along one direction, and then it is going to switch directions randomly after that time tau p. Okay, and they were able to show that this combination C F naught square tau p is a unique identifier of the amount of activity in the medium. And so this data, the mean square displacement as a function of time, this is computed for various concentration, various active driving force, various tau p, and but for all of them the product is exactly same. And then you see the mean square displacement is exactly same. Okay, so this tells you that this activity in the system can be controlled by many it can be from various sources. Okay, so but also it is known, and in somewhat later papers they are able to show that this is valid in a window which is where C F naught and tau p are probably small. Once you make it very large, then this may not be the correct description. Okay, so we took it up, and so along with my colleague in Hyderabad, Saroj Nandi, who also works extensively on developing theoretical aspects, particularly extending the theory of glasses to active matter and active glasses. So he recently extended one of the well-known theories of glasses. This is called random first-order transition theory to in a situation where you have active particles, and he was able to propose that you can come up with an concept of effective temperature, which has a very simple description. So effective temperature will be nothing but your parent temperature plus a force, the active force that you are applying with a constant factor k, which you can determine from the data. And the physics of all the physics that you could see in these active glasses can be understood within this framework, and so this is the test of that. So what we computed the typical correlation functions, 2-point correlation function at various activity, and let's say you take and then compute as a function of temperature as well. So you have two axes, one is activity axis, another is temperature axis, and you compute relaxation time, let's say for a given activity as a function of temperature. Then you fit this data once with certain form of behavior. Here we took mode coupling theory proposed form, which is the power law type divergence, where this T is replaced by T effective. Okay, so T effective, remember, has only this difference. So this is the extra term which comes in picture, and F naught is what controls your activity. So once you do that, and then you can extract out this constant prefactor k, okay, this kappa, and for one set of data. So once you get it, then you vary your F naught and T and do everything. And so this is the comparison. So you have for this relaxation time as a function of the activity for various temperatures. So one of the curve is fitted, but the rest is basically an outcome where you just change F naught. And you see that it matches beautifully with these lines are the basically predictions. These are not fits. So these are predictions, and the symbols are the data from simulations. So it clearly tells you that effective temperature descriptions very well describe your at least relaxation profile. And you are able to also show that if you go to significantly large activity limit where almost all particles are active, even there it works, but there are some deviations here which tells you that maybe you are shifting to a new regime. Yes.
So this activity parameter, it also has this persistent time and all.
Yes.
But here why you are considering the F factor, the persistent?
No, in our this particular case, the tau p is kept constant, and we also kept the concentration of particle fixed. But what we are able to show that, so even if you change concentration, also this so this is where changing the concentration, and we did not refit the data. We just took the same kappa constant, and it continues to explain you the relaxation time with increasing concentration of active particle. So only at very large concentration, while let's say is 100%, then there is some deviations, and yeah, we still do not have a very good idea about what may be wrong here. And yes.
These are hard particles.
This is Lennard-Jones type. Yeah. Yeah, by disperse. So then what we wanted to look at is 4-point correlation functions, and we want to ask this question: is this in the 2-point level? We see that effective temperature description works really well, and is it true in the next order correlation function? And there is no reason a priori to accept or expect that this effective temperature description may work or may not work. And indeed we see that it doesn't work. So what we looked at just to compare amongst these various active systems, we looked at, so we fixed relaxation time to be same. So for example, that's the reason which tells you that the peak of the chi4 is exactly more or less in the same place, and we chose F naught and corresponding temperature in such a way that the relaxation time remains constant. And you see that for a given active concentration of active particle, here it is 10%. So as you increase the activity, the chi4 peak goes up very systematically. Okay, and so this is the part which comes from mode coupling theory extension, which I am going to describe later. And even if you do it for let's say 100% active particle, there also you see exactly the same trend. And notice there is one interesting feature at a small time scale. There is extra peak which is coming out, and so that one of my students who is when he is going to talk tomorrow, he is going to focus on that aspect. So this is a very interesting aspect of this active matter. I'm just telling you that this has to do with phonons, and somehow in active glasses phonon get excited so much that it can actually wash out all the information that you get from using this kind of analysis, particularly in 2D, where due to Murphy-Wagner theorem, phonons will be already making havoc in your system, but in active glass it can be worse. So it can give you chi4 whose height can be 400, 500, but it has nothing to do with the glassy dynamics. So what this slide tells us is that even if your relaxation time is fixed, so that means your effective temperature is exactly same, right? But then your chi4 peak changes with changing activity, and this is true whether you change your. So we also looked at persistence time with some few more different persistence time, and there also it works. So only once you go to very large persistence time, then the dynamics changes and you have intermittency, which I think Pinaki, Madan, Chandan and Rituparna showed. So we are in the regime where tau p is still small. Okay, so then the question was that if your chi4 peak goes up so much with increasing activity, what can be the source of it? Maybe the heterogeneity scale is changing, and that's what we wanted to compute. And this is probably one of the first attempt to compute this correlation scale in active glasses. So there are 4 different methods we implemented to extract it, because we are using these methods are all tested in equilibrium setup, but you never know whether they are going to work in non-equilibrium scenario as well.
What is the definition of chi4?
Chi4 is basically a product of, so it is a 4-point correlation function. So you take 4 density product minus product of 2 densities average. Okay, so this at yeah. So this is the definition. I have to go back little more. Yeah, here. So this is the 2-point function, which is basically a 2-point density autocorrelation function, and you compute the standard deviation of that fluctuation. Yeah. So this method is, so I'm going to go give a little details about this analysis, which is called block analysis, which we developed for 4-5 years ago, and showed that this is an alternate finite size scaling analysis with a much better statistical control. And then the second one is by looking at a non-Gaussian tail of Van functions, and you can do a systematic scaling analysis there as well, which is very similar to this block. And you can show that there is a crossover length scale if you coarse grain your sample system, and then it eventually goes from non-Gaussian to a Gaussian behavior, and that crossover scale gives you the heterogeneity length. And then you can also look at the displacement field and the correlation between displacement field, which also give you the same length scale. And the last one is basically looking at the Q dependence of the 4-point correlation function and doing basically a liquid state theory analysis and to extract out the scale. Okay, so the first method is block analysis. What you do, you just take the somewhat bigger system size and subdivide the whole sample into smaller box, and you compute basically chi4 in all sub box. So now you have basically, and then you can average over many such possible sub boxes, which makes the data very, very smooth, which is very, very difficult in general if you do it for by doing simply canonical simulations. So one more advantage of this analysis is that each sub box can be considered as embedded into a bigger background, so which makes it to be in a grand canonical ensemble, which helps it to have extra fluctuations which are supposed to be there in chi4. For example, density fluctuation, temperature fluctuation, and concentration fluctuations, which are all taken care of by itself by doing only one big simulations, or one or maybe a few, and then you can do basically look at how chi4 changes with changing subsystem. And this is the data, and this is the corresponding data collapse, which you must agree that the collapse is really beautiful, which is very difficult typically to get. I don't know what happened to this data. Somehow there's a loss of resolution. And so you can compute extract length scale using this analysis. Then we also looked at, as I said, the 4-point structure factor and Q dependence of it, that if you use the liquid state theory Ornstein-Jarnik relation, then you can extract out as well the correlation length. So and then you can do this data collapse of the whole thing. This is the data collapse, and so if you draw a line along this, so that will be exactly this function, okay, is a Lorentzian. And so this is the basically displacement correlation in space, and you see that if you increase activity, indeed the correlation becomes longer and longer range. And so this is the length scale data as a function of relaxation time for various activities. And you see that when you are at high temperature window, so your length scale itself is small, and it doesn't depend too much on the activity. But as you go to lower and lower temperature, particularly let's say in a relaxation time order of 1000 only, which is not too super cooled. So you see that this black is the passive scenario, and this is the active scenario. And typically this dynamic length scale changes over the whole window by factor of maybe 4 or 5, but in the active glasses it changes by factor of 30, which is basically unheard of in this kind of glassy systems and in the glassy literature. And if you look at even the cluster formations, it is clear at the same time scale the passive has much smaller cluster than the active. So we chose parameter, this cutoff parameter to be such that the scale in the passive case is much smaller, but then otherwise it will be almost completely filling the space. And so some analysis also tells you that so that this length scale over this window has some sort of a power law type divergence type behavior. And the most interesting part is that the exponent changes significantly with changing activity, and this divergent exponent changes changes by a factor of 2 almost, which is very particular, which tells you that indeed there is a scale which is growing very rapidly. So then we wanted to ask this question, that is there some theoretical way that one can explain why in one occasion effective temperature works, but once you go to higher order correlation function it somehow fails. So this part of this work, all the credit goes to my colleague Saroj, who is the expert on mode coupling theory. So he extended this theory to capture some aspect of active forcing. So basically this starts from continuity equation of density and the momentum, and then you feed in both thermal and active noise statistics, and the free energy functional was taken as Ramkrishnan Yusuf, and then you can derive the time evolution of the density field. So this is with the full time and the momentum description, which is very difficult to handle numerically. So then if you just take the schematic equation, where phi is basically the density, and the k dependence has been suppressed or integrated out, and then you can compute 2-point function, which is basically phi correlation, and after all the algebra which is there in our paper, so you can write down 2 equations. One is for the correlation function and one is for the response, okay. And then the correlation and response will be connected by this effective temperature description. So up to this is perfectly fine. Now if you want to compute the susceptibility, this is following this concept of inhomogeneous mode coupling theory, where you basically perturb the system and try to look at the response. So basically what will be the response of a 2-point function under a given field, and you take the limit field going to 0. So that basically gives you, instead of a 4-point, a 3-point correlation function, which has been shown that has the same scaling behavior. So we looked at the chi, the 3-point correlation function, both for the correlation function and for the response. And you see that so these two have non-trivial dependence with each other, and indeed effective temperature comes in a way to recover the same phenomena that we see in simulations. So even though effective temperature is basically same on all the cases, and the correlation functions will exactly be same, this is the MCT calculations, but their chi4 or basically the higher order correlation can be very different. So it's not a complete in complete violations of this concept of effective temperature, but one need to understand from a more microscopic point of view. And just simple translation of saying that although the effective temperature is same, but the chi4 peaks are different, and then the effective temperature description is not working, is not a completely correct statement. But we are able to show that at least the physics of these active gases, particularly the dynamic heterogeneity, is very different from passive gases. And so now I am going to change direction a little bit and then again come back to this concept of growing scale in active gases. But before that, you need to basically understand some dynamics in the passive gas as well. So how much time do I have?
Less than 10 minutes.
That should be fine. Okay, so what we looked at, and this is primarily the work by my graduate student Anup, who is finishing. So what we wanted to understand basically how one or two elongated object evolves in this glassy medium, and try to basically ask this question that I won't be bothered by the background glassy medium. I want to only probe these 2 or 3 rods and their statistics, and I want to ask can I develop a theoretical understanding of those rods, and maybe they will help us to understand the medium as well. So with this we looked at basically glass forming, so took the same glass forming liquid. This is all in the passive case, and then we put 2 elongated probe particle and look at their rotational and translation dynamics. So first part will be rotational dynamics. So in the translation, some of you know that you can compute something called non-Gaussian parameter, but when you go to rotational dynamics, there is equivalent non-normal parameter that you can come up with, and this is the work of K.L. Sebastian. So there's an exact calculation done of a Brownian rod, and then he showed that this is the correct non-Gaussian parameter in some sense, which in a Gaussian in a Brownian limit will be exactly 0, but if it is beyond the Brownian or non-Fickian, then this is going to show interesting property. So this is in 2D and 3D has different forms, and U is the vector along the rod length. Okay. So if you compute this alpha 2 and alpha 2D and alpha 3D, because this is in 2 and 3 dimensions the forms are different, then you see that this non-normal parameter basically goes up and so the peak at some time scales. And so the moreover what we were particularly interested to know is now if I change the rod length, because this is one of the crucial factor in this analysis. So I want to not only look at the rod, but I want to look at how the dynamics get affected if I make the rod to be bigger and bigger. Okay, so how rod length comes into picture. So what you see is that for smaller rod length, this alpha 2 has a larger peak than when you go to larger rod length. So systematically the peak goes down, and so if you only plot the peak height as a function of rod length for various temperature, then you clearly see that at higher temperature the dependence is much weaker, but as you go to lower and lower temperature, dependence become very strong. And all of them are supposed to go to 0. So if you do a simple scaling analysis by scaling the x-axis only, then you should be able to collapse the data, and indeed that you can do. So you just basically scale the x-axis and all the data was able to collapse. So then you extract out a scale. So because your x-axis was a scale, and the thing that you divide, that also should have the same dimensions of a scale. So this scale turns out to be the same length scale, the dynamic heterogeneity length scale that we extracted before. Okay, so this is the comparison. So the black triangles are the length scale that was computed by this chi4 and all other methods. And so this is the red dots are the length scale that is computed by this probe rod. Okay, so this you can do it in both 2 and 3D and various models, and everywhere it perfectly captures it.
This kind.
Yeah, but also translate. So it has both. Yeah. No, in this case, the rods are much longer than yeah. So this rotation will not be yeah. But I think if you make them very thicker and with some structures, then you have to worry about them as well. And then we wanted to look at first passage time distribution of this rod in the rotational dynamics. So what do I mean by that? So let's say I choose an angle which is theta c, and I ask this question that but at t equal to 0, so how long does it take to go from one orientation and cross, let's say, an amount by theta c, okay? And as this rod is basically symmetric in both, so there is no head tail asymmetry, so it can be on this side the theta c, or can be other side as well. So this you can think of as Brownian motion with two absorbing boundary conditions, okay, and that changes the statistics a little bit, but this can be solved exactly. This has been done in many books, and if you look at it, the first passage time distribution has this is basically an approximate form, but so there's a series expansion form that you can write down. So this has a power law part and an exponential part. And so this is basically Brownian simulations with one absorbing boundary condition, and that will have t to the minus 3 by 2 power law. But if you have a two absorbing boundary condition, then you basically get back to this form, which there are many experiments where they get something similar, but this was proposed as a log normal distribution, and which you can show that it is not. And so this information is very crucial, because we want to now look at this first passage time distribution as you go to lower and lower temperature, and what is the effect of supercooling. So this is the unscaled data, and for various rods. And then if you scale basically the time is typically scaled by the moment of inertia of the rod, and you can actually collapse them on all top of each other at high temperature, which tells you that the rods are basically a simple Brownian particle. But as you go to lower and lower temperature, even after removing this high temperature behavior, there is an extra wing that appears, and as extremely low temperature, the wings become very, very prominent. And so we use this asymmetry in the distribution to characterize and find out how this underlying correlation can be picked up. So we looked at basically the skewness of this distribution and plotted as a function of the rod length for various temperature, and again you can do a scaling collapse, and the corresponding scale turns out to be the static length scales, and that we have computed by various methods, and I can discuss with you later, and all of them agree to each other. So basically it tells you that once you compute the first passage time distribution, and if you can also able to vary the probe length, then you have this information of both static and dynamic, and you need not probe the glass itself. Only probing few elongated particles dynamics will give you all this information. So then we tried to dig up an experimental data. We could not, whatever we can find from the plots given. So it suggests that indeed there is some signature of this kind of excess tail in the low part of the relaxation time. Even in this is an experiment done in glycerol with various 2-3 probes. And so then. Yeah, it will take few more minutes. And so this was rotational dynamics. You can do the same analysis for the translational dynamics as well. So you can look at the center of mass diffusion constant and center of mass relaxation time, and they have certain size dependence, which are basically described by this long rod limit descriptions, which is comes from hydrodynamic interactions, and then indeed they obey this 1 over L with log corrections. But if you remove let's say a high temperature and large rod limit behavior in this, then you can see that so this is the rescaled version of it, where the temperature high temperature and large rod limit is been scaled such a way that they become 1. And then you see that for a smaller rod, started to see stronger deviation as you go to lower and lower temperature. And this again tells you that there must be a scale which is interfering again. And now you can do a scaling collapse once more, and you do indeed see that the same static length scale reappears in the translational dynamics. So this you can do the same analysis for the relaxation time as well, and you do recover the same behavior, and this is simply because the diffusion and the translation of the rod obeys the Stokes-Einstein behavior, which relates them via this perfectly. In all temperature, rod limb and the rod length conditions, the Stokes-Einstein is obeyed, and supercooling somehow did not affect it, at least this relation significantly. So that's why any one of the quantity if you compute, and that will help you to extract out the correlation. But if you look at the rotational or the translational diffusion along with the liquid dynamics and couple them and look at that statistics, there you see that there is a fractional Stokes-Einstein appears, and it systematically starts to show deviation as you increase supercooling. So these are a bit involved slides, and I have to really describe you how the analysis was done. But the point is that so you look at this D, the diffusion constant is of the probe, and the tau alpha is the relaxation time of the liquid. Okay, and they show deviation and a violation of Stokes-Einstein behavior, and you can do a detailed analysis to extract out and understand this violation simply again by the same dynamic length scale. And same analysis you can do for the rotational part of the dynamics. This is called Stokes-Einstein-Debye breakdown. So the rod itself doesn't obey, basically breaks this relation, but the rod with the liquid, the rotational Stokes-Einstein relation is also violated, and similar analysis explains again that the same underlying scale actually leads to this breakdown. So in a nutshell, what we are able to show that this underlying dynamic and static correlations basically will control all the dynamical features of any probe, and if you have a good understanding, then you will be able to even understand and extract out informations of the parent liquid or the medium itself. And so this analysis was missing in all the literature, because if you look at various experiments done on a single molecular experiment, so there they will do it for a given probe length, but not with varying probe length. So what we are proposing is that you take the same liquid but vary your probe, and then repeat this analysis to extract out the information. So this will be a direct information, and you do not have to assume any correlation. Okay, so this was the analysis, extracted data from some of the existing experimental literature, and indeed you see the same thing. So, and you can redo the same analysis to show that there is this correlation. This is for this trinitro-butyl or whatever, TNB, which OTP I know. And okay, so this part I can actually skip, and so now let me come back to these active classes once more. And what I showed before, there the correlation becomes very, very large. Now if I put the rod, what am I going to see? So what I see is that the same analysis holds true, but the advantage is that as the scale is very, very large, your scaling becomes even better. So it becomes nearly perfect. The scaling collapse, you see that there is almost no deviation with respect to each other, and indeed the scale grows by factor of at least 25 to 30, which suggests that the active glasses somehow picks up very strong dynamic heterogeneity, and this is something which will be good to have a future understanding. And similarly, you can look at some part of the translational dynamics and extract out the static length scale. Static length scale seems to be also growing very rapidly. Okay, so typically in passive glasses, within the same window of relaxation time, it grows by maybe factor of 2 to 2.5, but here it is growing by factor of 8 almost. And so we hope that some of this, as the scales are growing much bigger, maybe these theories of various theories of glasses can be tested in this context. But one big question will remain that we are using a non-equilibrium scenario to test the equilibrium theory of glasses and whether they are valid or not. So yeah, we already got a very bad referee report saying that this way you are going to kill the physics. But anyway, so let's not I think this again the same analysis with the Stokes-Einstein-Debye, and you can skip that. And so let me thank saying the funding sources. The most funding comes from TIFR, and this is by this number. And I have a co-research grant, and Smarajit is also acknowledged. And thanks for your attention.
Thank you. Yeah. Maybe one or two very quick questions, and then we can continue. Yeah. Okay.
Yes, so when you say that you put some rod-like particle to extract information, so do you need to, I'm thinking from experimental point of view, do you need to assume some sort of coupling or between those two, like?
This is not relevant actually. So as long as the two, if there are a few more rods in the medium, and as long as they do not aggregate. So if you put a very dilute amount of it and far away from each other, so that over your probing time scale they do not aggregate, then how the rod interacts with the medium is not going to change your statistics.
I see.
Yeah.
Okay.
So at least we varied interaction parameter, and these things do not.
Doesn't have an effect. Okay.
No.
Thanks.
Yes, Madan.
Smarajit, this dynamical heterogeneity discussion that you had for the, so yeah, can you just show the slide about the, when you had the displacement correlations?
Yeah.
And you had some, what are the structures that they are the low displacement particles, is it?
These are, yeah, so these are the, I think the lowest.
The lowest, so they stuck.
Highly, not the lowest ones, yes.
The lowest ones, so these are caged particles.
Caged particle,
okay.
yeah, basically.
And so do you have any understanding of why is it so much bigger and fractal-like? And
but here we have to use some, this is for visualization, I won't take it too seriously, because there is cutoff that you have to put in by hand.
No, but compared to the passive one is very distinctly different. So
yeah, just, but also as I said that if you change cutoff, then things are going to change very differently. This is just to show you, I don't want to draw any conclusion of fractalness of any of the structures.
Okay.
Yeah,
no, I was thinking that you're trying to hint at some underlying feature which is different.
So what we are basically convincingly say is that the correlation becomes bigger.
Okay.
But whether these correlated regions are of fractal-like or not, that I think unless I do a careful analysis, I don't want to.
Yeah. And in the mode coupling theory, I thought you were going to say that activity will enter as will have contributions there which are apart from the T effective. But the only way activity enters into your final mode coupling equations is as a T effective, no?
So at least in this level.
At this level,
and after that, it actually gets convoluted with many things in the second order. So first order, that's why you have very clear T effective description.
At least for small tau.
Yeah. And
the next one, in the next order?
In the next order, T, this actually goes into in a various terms here, and in a non-trivial manner. So it is not a very simple one-to-one correspondence you can draw.
Wow.
And so it doesn't tell you in a way to find out a different T effective. That also it doesn't tell you. It basically tells you that if you look at this MCT-like theory, and if the relaxation dynamics is controlled by an effective temperature, the chi4 will have the response that we are seeing in any simulation. I think it's not going beyond that. Yeah. So it is not going to give you a prescription of how you can redo and come up with a different effective temperature.
Maybe you have already discussed, just a small question.
Yeah, yes.
So in case of this active glass, you talked about this length scale. So your system has got also temperature. So you have the two sources of fluctuations. One is the temperature and also the active forces. So the length scale that emerges for this case, how to extract the contribution? Is it possible to separate out the contribution that is coming from the thermal source and on the active force?
So one can in principle do basically a thermal active glass as well, and there also you are going to see this length scale is going to grow significantly. But decoupling them will be a bit difficult. At least I do not have any clear way to find out how much is controlled by, no, I don't know.
Okay, thanks.
So following up on what Father was asking.
Yes.
So for your active glass, if you were to look at the clusters
not the pattern, just the shapes as you evolve towards the height of alpha. Do you see any qualitative changes in the way the shapes are? Of these, because the random first order tells you that something should happen across MCT. Will you see that here, or?
We haven't looked at into kind of that angle, and somehow I am not a very good fan of proposing that the shape significantly changes from string-like to a compact object, and because this always involves some sort of some invoking certain arbitrary scales to define what do you mean by part of the cluster, but the other interesting thing that you see typically that below mode coupling temperature it goes down.
Yeah.
So that is something which we would like to understand in this
that's
context.
seen in the experiments by Angelini also.
Also, yeah.
They come down, but
so
they
you want to actually go push it beyond that and then find out indeed whether it comes down or not. So, but the next step.
Yeah.